Okay, class, today we're going to talk about solving exponential equations, and this is a topic that was covered in Algebra 2. But before we start with the video, I'm going to be relying heavily on the notes. So my suggestion is you go ahead and either print out or copy down page 101 as well as page 100, because there's some blanks in there that we're going to fill in this video, and it's helpful if you have the pages already printed out or on there so that you can fill in the blanks as we go through this video. Okay, so we're talking about exponential equations, and before we can talk about solving them, we have to remember some properties about exponential equations. And if you remember, we have a whole selection of properties that we're going to go over. Okay, so let's start talking about that. Now in this case, A and B are real numbers and M and N are rational numbers, which are the numbers that can be written as a fraction. And A and B are going to be used as our base numbers. And I'm just going to say for an exponent, base. Our bases are A and B. And then our powers, or the exponents, are going to be in M and N. So in the power function, the exponents are going to be the M and N. So it's important that you know the difference, because what's going to be staying the same is pretty much the bases, and what can be changing are the exponents. Okay? So now what we're going to do is we're going to take a look at some common properties, and we're going to fill in the blanks, which you should be able to fill in the blanks too, because you remember it from probably middle school. No, Algebra 1 and definitely Algebra 2. Okay? So the first product, a to the m times a to the n, is equal to a to the m plus n. So if the bases are the same, we simplify the expression by just adding the exponents. So a to the m times a to the n is the same as a to the m plus n. A to the m raised to the n, which means we have a power raised to a power, is the same thing as keeping the same base but multiplying the exponents to get the new exponent. And if I have a power of a product, which means I have two numbers as the bases, then I can basically distribute by doing a to the m and b to the m. So it's kind of like the distributive property. Okay? And then we have the next. Now this is very important. A lot of people seem to forget that. But the negative exponent property is a to the negative m. If the exponent is negative, it doesn't mean the power is negative. It means that negative means to flip it. Okay, so that's very important. It's basically saying flip the base. So instead of a to the m, it's the reciprocal of the base, which is 1 over a to the m. Okay? And this is all for all a, as long as a is not 0. Then we have a popular property that, if you remember it, life is to be very easy. These two are really the two of the most important ones. A to the 0 is always 1. I don't care what the base is, as long as it's not 0. The base can be 3,955, but if the exponent is 0, the power a to the 0 is going to be 1, regardless. Okay? And then the last one, not the last one, but the quotient of properties, a to the m divided by a to the n is the same thing as a to the m minus n. We're basically subtracting the exponents. And all these work as long as a is not 0. Okay? And last but not least, oh no, still not last but not least, we can also distribute as well. And here's the last one. If m and n are positive integers, or if the exponent is a fraction, another way to write their fraction is to separate a to the 1 over n, which is anytime the denominator is the radical and the numerator is the power. So we may get to some problems like that as well. Okay, so now why is this important? Because we're going to use this to solve something very important. So an exponential equation is an equation in which variable expressions occur as exponents. And so if b is a positive number, in other words, if the base is a positive number that's not 1, then b to the x is equal to b to the y if and only if x is equal to y. So all that means is that if you have two exponents that are set equal to one another, then you can solve for the exponent if the bases are the same. So for example, 5 to the x equals 5 to the 4, then that means x has to equal 4. Okay, so how are we going to use this to solve some exponential equations? Well, this is where you're going to need page 100 in your notes, because we're going to do some sample problems, which you guys have asked me to do in the video. So here we have an example on page 100 solving this equation. In order to solve this equation, remember from the previous proof, we can only set the exponents equal if the bases are equal. And as you can see here, the bases are not equal. 64 is not equal to 16. So right now we can't set the exponents equal until we can convert these bases so that they are the same base. Well, let's see. If you remember, what relationship does 64 and 16 have? Well, they all seem to be powers of 4. 16 is 4 to the second power, and 64 is 4 to the third power. So I'm going to rewrite those two because they all have the same base of 4. And then when I rewrite these two, then 64 to the x is going to be 4 to the third to the x, which is the same thing from the powers function property as 4 to the 3 times x. And 4 to squared to the x plus 1 by the power properties is the same thing as 4 to the 2 times x plus 1, or 4 to the 2x plus 2. Okay, and that's by the power property. So now that they do have the same exact bases, now I'll be able to set the exponents equal. So since the bases are equal, then that means that the exponents must be equal. So that means 3x has to equal 2x plus 2. And then we can go ahead and solve by getting x by itself, so x would have to be 2. Okay? And that's simple algebra to go from this step to this step. It's just algebra. Okay? So my solution is 2. How do I know if my solution is correct? Well, you don't have to ask Ms. Riggins. You can just go ahead and check it. Replace x in the original equation with 2 and see, do you get 64 squared? Is that the same thing as 16 to the 2 plus 1, or 16 to the third power? And when you calculate it, you'll see that it is the exact same. Okay? All right, now let's move on to a problem where they don't take a step by step. Okay, so here we have 3 to the 7x minus 3 is equal to 9 to the 2x. And as you can see, the bases are not the same, so we cannot do anything with this until we get the bases as the same. So what's the relationship? Well, 3 is not a power of anything, but 9 is the same thing as 3 squared. So I'm going to go ahead and over here, I'm going to replace 9 with 3 squared. And then I'm just going to be left with, I think, is that 3x? Yeah. Oops, sorry. Typo. 2x. Okay? So as you can see now we have the same base. Well, almost have the same base, because now I have to do the power properties. So let's see. I'm going to rewrite this as 3 to the power is 2 to the 2x, so that's 4x. We multiply the 2. Okay? So now that we have that, then we can say they now have the same bases. And then we can use the power property to go ahead and say that means that 7x minus 3 is equal to 4x. And then do our lovely algebra. We get 3x minus 3 is equal to 0. So that means x is equal to 1. And there we have our solution. And we can go ahead and check to see if our solution is correct by going in and seeing, does 3 to the 7 times 1 minus 3. So let's check that. And I'm going to change it to red so we can see. So it's 3 to the 7 minus 1, minus 3, which is equal to 3 to the 4. Is that equal to 9 to the 2? That's the question. And as you can see, 3 to the 4th is equal to 81. And, oops. 3 to the 4th is equal to 81. And 9 squared is 81. So yes, they are equal. So that means that my solution of x equals 1 is absolutely correct.